I don't see the chat window actually. Okay, in the end, I can try to see that. It's okay. Let me know when we can start. Hi, good morning, everyone. Saga, could you please confirm again if my slides are properly visible? Okay, hi, good morning, everyone. So, as you know, we will have 3 sets of lectures on radio astronomy, and in this, we are going to uh, explore like what are the things that we can do at radio astronomy, but not just talk about what are the things that we observe in radio astronomy, but we'll also talk about how we do radio astronomy, the kind of telescopes and the techniques that we use, right? So we will try to cover all of it in these 3 lectures, and in the last lecture we will also try to look at what are the new telescopes that are coming up, because that's something which is going to be very exciting. A lot of new science that can be done with these new telescopes coming up, right? So, as I will assume that you have already had in-depth lectures on radiative processes, and you are familiar with what kind of radiation that we expect from various astrophysical sources in the sky. And in these radio astronomy basic lectures, we are trying to focus on like how we can detect that emission, especially when that comes from the radio objects, right, at the radio wavelengths. So let us start. So what is radio astronomy? Radio astronomy is basically the study of natural radio emission which comes from celestial objects, right? So all the celestial objects that we know of, starting from sun, then to stars, and then in general, we can also talk about galaxies, and even cold glass clouds in galaxies, and cosmic microwave background radiation. All these astrophysical objects emit radiation at radio wavelengths at certain level, right? Some are much brighter at radio wavelength, some are fainter, but they all do emit radio waves at certain level. And the radio telescopes that are currently available are capable of detecting this emission, right? So this means that we can do all kinds of exciting astrophysics at radio wavelengths. Now, there are a couple of things to keep in mind. One is that even in radio astronomy, although we'll be talking about astronomy at lowest frequencies, but one could actually be discovering some of the most energetic processes and objects in the universe at these wavelengths, right? So one should not, so don't try to think of it that in that way that, okay, since we are operating at lowest frequencies, we will be looking at low energy phenomena. No, that's not the case, right? So that's a misconception which we should do away with straight away. So let us now start with some very basic overview, some foundation of like what radio waves are. So radio waves, like light, are electromagnetic waves. There's nothing more special about them. And the theory of propagation is actually based on Maxwell's equations. And Maxwell's equation is something you are all very much familiar with. You have Gauss's law, which tells you that net electric field through a closed surface is proportional to the enclosed charge. Then you can come to the second equation where you can see that like there are no magnetic monopoles. And then you come to Faraday's law and Ampere Maxwell law, which tells you that changing magnetic field is associated with a electric field, and electric current, and change in electric flux could be associated with magnetic field, vice versa, right? So these partial differential equations relate electric and magnetic fields and currents and changes of fields, right? That's something which we know, we know in depth. And a solution of these is a second order differential equation which describes the propagation of electromagnetic waves. That's also something which we know, right? And basically, these electromagnetic waves are nothing but these are E and B fluctuations that are perpendicular to each other and also perpendicular to the direction of propagation. This is it. So radio waves also obey all these things. And electromagnetic wave is something which we can represent by a complex number, right? This electric field vector here you can see, we can represent it like this, A being amplitude here, and phi is the phase term corresponding to it. So we can write it like this, and through our eyes or through photographs, what we are measuring is this quantity. You can see that E star, the complex conjugate term here, and the time average of this, represented by these brackets, right? So this is what we are measuring. That is the brightness and intensity of the radiation that comes to us. Now, the very important thing to remember, understand when we are talking about radio astronomy is that when electromagnetic waves or the radio waves are actually traveling, when two waves are traveling along two different paths, they would experience a phase delay, right? Even if I take a same wave and it's traveling along two different paths, it would experience a phase delay, right? Think of a situation which we encounter in Young's double slit experiment, right? We have two slits illuminated by the same source, but if we are looking at a point on the stream and the radiation from the two slits is actually traveling a different path, then it would experience a phase delay, right? And if two such waves superimpose each other, then mathematically we can represent that superposition like this, E1 and E2 being the two waves. And you can represent the second line here represents the superposition between them. And as a result of the superposition, we will see interference pattern, right? That is a set of bright and dark fringes, which is represented by this fringe pattern, the interference term here, 2A1 A2 cos phi, right? This is something which we know very well. So the fringe pattern on the screen is caused by the interfering term here, and this carries and this varies with the path length difference between the two waves that are coming, right? And it varies with the position on the screen also, right? So this is something which we have in fact done in Young's double slit experiment. Many of you would have done in your laboratories in your universities. So this is something which we have to really understand very well, that electromagnetic waves interfere, right? And this interference pattern that we see, it contains information about the spatial structure of the source, and it also contains information about the spectral structure of the source, right? So if there are two spectral lines, it would contain information about that. In fact, Michelson used this technique to specifically build a stellar interferometer, which he used to measure sizes of stars. And he also did spectral interferometry to study fine structure of lines. And use these techniques to standardize, in fact, meter the unit of measurement of length in terms of red line of cadmium, right? So this historically also this understanding that electromagnetic waves interfere has played a very fundamental role. And in 1907, Michelson was actually awarded Nobel Prize for the development of these instruments and various investigations he carried out. And the principles involved in these experiments, like Young's double slit experiment and Michelson's interferometer, and mathematically we will talk about it more in next lecture, the specifics of Fourier transforms, they are at the core of how radio telescopes work, right? And so this is one takeaway that you must have from these three, or I would say today's lecture, is that to understand radio astronomy, we have to really well understand Young's double slit experiment, Michelson's interferometer, and Fourier transforms. And if we understand these three quantities, these three concepts very well, then we can very much have a very good foundation to understand radio astronomy, and then it becomes a lot of fun, right? So, but before going into the technique of doing radio astronomy, let's talk about what exactly is radio window, like the frequency range that over which radio astronomy is done. So on your slide, currently what you're seeing is the entire electromagnetic spectrum, and radio astronomy is confined to this range here, right? Which is going from approximately 0.3 millimeter in wavelength. So in frequency, it corresponds to 1 terahertz to 30 meters. And the 30 meter corresponds to approximately 10 megahertz. So radio window actually covers almost 6 decades in frequency, right? If you compare this with optical window here, you can see that it's so extremely broad. And radio waves, the speciality is that since we are talking about much longer wavelengths, they can penetrate interstellar dust clouds and also Compton thick layers of nuclear gas and so on. So So radio waves are actually an excellent tracer of dust obscured universe, the parts of the universe which we cannot see at optical, X-ray, ultraviolet wavelengths. We can see them very well at radio waves. Now, another very important thing to realize is that unlike other parts of electromagnetic spectrum, the radio spectrum is very extensively used by mankind. And this is gradually changing actually, because slowly we are beginning to occupy more and more part of electromagnetic spectrum. But just talking about the radio window, all of us all of us have microwave ovens at our homes or even in offices. Everyone now uses mobile phones. We have Wi-Fi devices. We have FM radio and TV transmitters. Right? They are all sort of all around us, and all of these devices actually emit at radio wavelengths. So that's very important thing, that the signal that we are trying to receive from astrophysical objects in the sky are very, very faint. And we on our ground have surrounded ourselves with all these radio transmitters, right? So a very important thing that is part of radio astronomy is to build telescopes, radio telescopes at places where there is very little radio frequency interference. This means that you go to very far off places on Earth where there is very little population, there is very little modernization, far away from cities, so that you can find places where there is as little radio frequency interference as possible, so that you can, when you detect a signal from the sky, you are sure that it is actually coming from an astrophysical object and not just some terrestrial noise that you are picking up. And that's probably the biggest challenge that radio astronomy is facing currently. So now the second or another thing that you may ask is that why this radio window has these boundaries on either side here, right? Why is it that we cannot continue to go on either side? So these boundary are set by following two reasons. So the lower bound that you are seeing, which is by lower bound I mean at the higher frequency, at this side, which is that is coming from absorption due to various molecules in the atmosphere. So what happens that there are various molecules of, like for example, water vapors in the atmosphere, and they have they would emit they would absorb radiation that is coming from the sky. So it just does not come, right? So what this graph y-axis here is the transparency, right? So of EM waves. So you can see that like it's here it's like the transparency is like almost zero, right? And now you can ask the question that what is happening at the other side of it? That why is it that we cannot receive radiation on the upper side of it? Now the upper bound is related to what we call as plasma frequency, right? So if you know Maxwell's equations and you have ever solved it for what is called propagation of EM waves through plasma, then you would find that it sort of gives you a solution which relates to what is called plasma frequency, right? And what this means is that only those waves which are allowed to pass, which have frequency higher than the plasma frequency. At frequencies below the plasma frequency, the refractive index is negative, so waves cannot propagate through, right? So this plasma frequency sets the lower, the cut or the lower cut on the frequencies of electromagnetic radiation that can set to plasma. You must have read in your textbooks very much that the metals shine by reflecting most of the light in visible range, and this is also related to the concept of plasma frequency, because what happens is that visible light cannot pass through the metal because the plasma frequency of electrons in the metals actually falls in ultraviolet range. So frequencies in ultraviolet, at these frequencies, metals are transparent, right? If you shine ultraviolet, it will pass through, but if you shine an visible light, it will not pass through, right? So that related to the concept of plasma frequency. So Earth's ionosphere actually reflects radio waves for the same reason, very much the same reason, right? So what happens that if we are observing, if you want to observe at frequencies which are lower than say 10 megahertz, which corresponds to the plasma frequency of ionosphere, and this is the electron density that we're talking about for ionosphere, then in that case, the radiation that is coming from the space would be reflected back, so we cannot receive it anymore. And this idea that ionosphere reflects radio waves of certain frequencies is also used for terrestrial telecommunication, right? So this is also a very useful thing. But for astronomy, radio astronomy, it sort of sets a barrier that up to this frequency we can do radio astronomy from ground. If we want to do more, we have to go to space or build radio telescopes on moon, right? Which is what also been done. So this slide, I'm sure you would have seen it in many other presentations and lectures too. What this tells you that each wave band actually occupies a unique place in astronomy, because it gives you a different view of the same astrophysical objects, right? And it's very important to be able to look at these different astrophysical objects at different wavelengths or frequencies, because then it gives us an additional information. It's not a duplication of information, okay? Because, for example, if you look at various panels in this, and if you look at the top panel is radio continuum image, which is at 408 megahertz. It's a very low frequency, you can see. And the second panel is actually corresponding to a spectral line, right? It's a spectral line of neutral hydrogen, and we'll talk about it more in later in the lectures. So it is corresponding. So this one represents actually the distribution of atomic gas in our galaxy, and the top panel is actually representing the diffuse radio emission in our galaxy. So these are very two different physical processes that we are talking about. In first one, probably electrons are getting accelerated in electric field or in the presence of a magnetic field. So these are two different physical processes you must have come across, like free emission or synchrotron emission. In the second one, it's actually the hydrogen atom in which its ground state, it has whether it has electron and proton spin parallel to each other or opposite to each other, the energy state is different, and corresponding to that, when the atom transitions from one state to the another, there is a radiation here, right? So that's what we are seeing in this case. And likewise, if you see in the other panels, you can see that some are corresponding to infrared, mid-infrared. These will be corresponding to older massive stars in the galaxy. If you come to optical and ultraviolet, you start seeing that not only we do see some bright patches where we can conclude that there are stars, but we also start to see these various dark patches, right? And these dark patches, when you compare it with other panels, you can quickly infer that it's not that these are dark because there are no stars in that region. They are dark because there is dust in those regions, and that's something which is getting blocked because we are now observing at optical and ultraviolet, and of course these wavelengths are much shorter and they're getting blocked by dust which is present in the interstellar medium, right? So that's so when we put all these things together, then we begin to have a more complete picture of what is actually taking place in an object. So now let's move further. Now we are talking about, let's talk about how radio astronomy actually started. And that takeoff was not very smooth. That's something you can see, like I have written bold in my slide. And let's try to understand why it was not a very smooth takeoff. And it's also a very important, there are several important learnings in this for us to take away. It tells us like how to actually, how theory and observations go hand in hand, and also how the kind of important considerations we should have when we are setting up an experiment. So let us start with something which we all know. Right? This is a very standard slide and a standard question that almost whenever we are having an interview or something, we have this question like, okay, something based on black body is always there, right? So this is by looking at it, you would be knowing straight away like what we are talking about here. So this is a black body spectrum or the thermal spectrum that we are talking about. So this is just the kind of radiation a body would give by virtue of its temperature. And what you see here is the Rayleigh-Jeans limit of it. It's simple. Just keep this approximation in mind, because at radio wavelengths, we are talking about very low frequencies, right? So we can very well work with this approximation in that case. So, but before proceeding further with this, let us try to understand, like, if we are looking at thermal objects, then what kind of what's the strength of signal that we are anticipating from them? Okay, so if you look at sun, right, it's a black body, and if we take sun and put it at 1 parsec, why 1 parsec is of interest here? Because that's the distance to a Proxima Centauri, the nearest star that we have. It's a 1.3 parsec. So if we put our sun there, then it would give a signal of approximately at radio wavelength 0.3 macrojansky, right? So 0.3 macrojansky, you can guess is that like it's pretty faint. 1 Jansky is equals to 10 to minus 26 watts per meter square per hertz stadian, right? That's the unit of Jansky that we have here. So if this is such a faint signal, and you can believe me here that 0.3 macrojansky is pretty faint even for current telescopes that we have, right? It would take like many hours of integration. It's not impossible, but it will take a lot of integration time of the current telescopes to be able to detect that. So right, so that's the kind of signal that we are talking about from a thermal black body, like a star, right? So just keep this idea in mind that if we put sun at just 1 parsec or a star at that kind of a distance, it would be a kind of a hard to detect for us. Okay. So how the radio waves were detected? So radio waves were detected quite serendipitously, right? And why that happened? So let's go back a little bit in time. So we know that like Maxwell's equations were written in like something like 1860s, right? And infrared and near UV radiation was already detected by then on ground, like at 1800 and 1801. And if we go to Hertz experiment in 1887, then radio waves were also detected. So it was known by then that, okay, these kind of radiations, like electromagnetic waves at different wavelengths do exist, right? And as soon as these were detected, then many people started thinking about straight away that we can actually also detect these from astrophysical objects in the sky. But in those days, the understanding of astrophysical objects was such that people were mostly observing stars, right, sun and nearby objects at optical wavelengths. And the major understanding at that time was that the objects that are there in the sky are actually black body. So this is the physical process through which they are emitting radiation. So this is the kind of spectrum that they would emit, right? This is what was the astrophysical understanding of the objects at that time, right? So what Jansky, an engineer at Bell Labs, was doing, so Bell Labs was setting up some transatlantic radio communication. So Bell Labs wanted to investigate, and they gave Jansky this task that whenever they were doing this communication, there was always some kind of a noise in the signal. So Bell Labs told Jansky, was an engineer working there, that can you please investigate that what is the source of this noise. So what Jansky did, that he built an antenna, which you can see here on the slide. This was operating at 20.5 megahertz, and it was mounted on a turntable that allowed it to rotate, so that you can then scan different parts of the sky. That was the idea. So by rotating the antenna, the idea was that he would be looking at different parts of the sky, and then he would try to see like from where this noise is coming from. And the antenna was rotated every 20 minutes, right? And after recording signals from all directions, and this he did for many months, he identified 3 types of sources of static noise, right? One was nearby thunderstorms that were taking place. Then some thunderstorms which were further away. That was the second source he identified. Then he also identified a very faint, steady hiss, kind of a continuous noise kind of thing, which was coming through. And he spent over a year investigating this third type of static. Because the peculiar thing about it was that it rose and fell once a day, right? Every day it would rise and then it would fall, right? So initially he thought that it is probably coming from sun, right? Because that's the kind of thing brightest in the sky. So he thought like maybe that's where it is coming from. But after a few months of following the signal, this brightest point actually he found that is moving away from the position of the sun, right? And then he also noticed that the signal is not repeating exactly at 24 hours. It's actually repeating after every 23 hours and 56 minutes. And you must be knowing what is this characteristic of. This is the characteristic of fixed stars in the sky, right? So 23 hours and 56 minutes is the duration of the sidereal day, right? Not the solar day, right? And that sort of proves that this signal is actually not coming from anything terrestrial, but it's coming from an astrophysical source in the sky, right? So, and he eventually figured out with more investigation that the source of this static is actually coming from the Milky Way, actually the center of the Milky Way galaxy, right? Which is in the constellation of the Sagittarius, right? That's why it was shifting slowly over the year, right? That's what was happening. So this is the first detection of radio wave from an astronomical source made by Jansky, and this discovery was very, very widely publicized. It even appeared on the front page of New York Times. This was in 1933. And Jansky was very excited by this, and he wanted to actually follow up on this discovery and try to see like if this kind of emission could be detected from other things, and maybe even study Milky Way galaxy using this radiation. And he actually proposed to Bell Labs that he would like to build a even larger antenna, and then he can do a better job with that. But the employer decided that no, like our job was to actually identify where the static is coming from, and we are not like sort of interested in doing astronomy with it. So Jansky was then assigned to do other things, and he did no more radio astronomy after that. Right? But the fact that he made this fantastic discovery, which led to the start of radio astronomy, in honor of this, the flux density that we measure is done in the units of Janskys, right? That's the origin of why we measure flux density at radio wavelengths in the units of Jansky. So discovery was made, but it didn't lead to sort of big scale radio astronomy. But it led to many scientists being fascinated by like wanting to do this kind of a thing. And one person who actually was very highly motivated was Grote Reber. This picture you can see on the left. And he thought, like, since Jansky made the discovery at Bell Labs, then why not I applied to Bell Labs that I would like to do this kind of experiment. So he applied, but he was denied. And we know that the Bell Labs was not so much interested in radio astronomy itself. So then what he did, he was so motivated that he took up a job as an engineer somewhere, right? And then but in his own time, in his free time, over the weekends, in the evening, in his own backyard, he built this large telescope, right? 10-meter parabolic reflector, not a small telescope by any means. He built this on his own in his backyard and started doing astronomy. So he started observing different parts of the sky, and then he thought, right, now we go back to, right, this slide. If you recall that we looked at this, that this is the black body thing, and you now also know that, like, Dr. Reber also knew that Jansky did this experiment at 20.5 megahertz. And if you go to this plot, you will see that as I'm going to higher frequencies here, the radiation is increasing further, right? The strength of the radiation, I mean. Okay. So he thought that if Jansky did it at 20.5 megahertz and detected signal at certain level, then if I carry out my experiments at even higher frequency, then I should be able to see it much stronger, and that way I can detect more details in them, right? So that's what his idea, and fair enough, because that's what he thought at. So his initial observations were at 3300 megahertz, which is 3.3 gigahertz, but he detected nothing, right? Then, but he did not give up. He thought, like, okay, let's try again, because when you don't detect something, you first try to see, like, okay, let me look at something which is maybe wrong with the instrument, or so you try to go closer to what someone else may have done to see, like, if you can reproduce it at some level. So he moved down to 900 megahertz. So this is not exactly at, it's still much higher than what Jansky was doing. So he still did not detect anything. But then he eventually moved even closer. He went to 160 megahertz. And then he confirmed Jansky's discovery, right? And then he further observed various objects in the sky at 160 and 480 megahertz. So these are like examples of multi-wavelength astronomy in those days you can think of. These are multi-frequency observations, and he observed these different objects like Sun, Cassiopeia A, Cygnus A. These are some of the brightest radio sources in the sky. He observed them, he published results in FJ. So you can think of him, not just think of him, he is the first professional radio astronomer. And one very crucial finding of this study is that, contrary to expectation that radiation strength would be increasing as I'm going to the higher frequencies, he actually found that the radiation strength is actually increasing as you go in the opposite direction. That is, as you go to the shorter frequencies or the longer wavelengths, the strength of the radiation is increasing. So this straight away led him and other people to conclude that this radiation is actually coming from a process which is not thermal, right? Which is not because of the virtue of the temperature of that gas or that body, right? And straight away, since this was not thermal, they called it non-thermal. And around the same time, the theory was theoretical development was also taking place, and it was found, it was suggested that it is actually coming from electrons gyrating in the presence of magnetic field, right? So this is a synchrotron emission due to relativistic electrons in magnetic field. And astrophysical objects, for example, like our galaxy, has plenty of relativistic electrons, and it also has magnetic fields everywhere. So this problem was actually resolved by a Russian physicist called Ginzburg. He showed that electrons moving at speeds close to that of light, which is like the relativistic electrons in the magnetic field of galaxy, they would actually, their trajectory would be a path similar to a helix. So this is a problem that all of you have solved already, I think. And part of the motion of the electron is the circular, and so this is equivalent to electron being accelerated, and that's how this radiation comes through. So this is this radiation is called the synchrotron radiation, right? So this is the non-thermal. So this is discovery of a new physical process as well, right? So this is one thing which I wanted to highlight to you, that whenever we plan an experiment, we of course proceed with the basis of what is our current understanding of the physical processes, and based on that expectation, we try to set up our experiment, right? Growth river, based on the understanding of thermal process and what Jansky had done, set up his experiment, but he did not detect along his expectation. So non-detection in this case is a motivation to then investigate deeper. So he then challenged his understanding, and he set up an experiment which then demonstrated that actually the radiation is coming from a physical process which was not known at that time, right? So this is fantastic. So since then, so you can think of this as the set of events and the time when radio astronomy actually took off at that time, then, especially after Second World War, when the timing was right, when people started doing radio astronomy, institutes and observatories started getting set up. So we are talking about 1950s here. And since then, radio astronomy has produced some of the most fundamental discoveries in the field of astronomy, and that have influenced and altered our view of universe at that time. And so let's look at some of them before we jump into techniques of how radio astronomy is done. So let's start with AGNs and quasars. Quasars, the most powerful type of AGNs. You know that how quasars and AGNs radiate, like they have a supermassive black hole in the center of the galaxy, and that's accreting matter, and that gravitational energy then converted into this huge amounts of radiation, and that's how we see these AGNs. These are extremely luminous sources in this universe. Initially, when they were discovered, they challenged the basic discovery of the universe at that time. So quasars and AGNs were first discovered at radio wavelengths. Now, of course, we know millions of such AGNs, but when the first discoveries were made in 50s and 60s, then this happened at radio wavelength. Then discovery of H1 21 centimeter line, and you know that hydrogen is the most abundant element in the universe, and to have a transition or a probe, which is this 21 centimeter line, which can allow us to look at neutral hydrogen at all kinds of places in the universe is really invaluable, right? So theoretically, this was predicted by van der Hulst in 1944. What had happened that after Jansky's discovery, and then wrote a reverse paper in Astrophysical Journal, which was sort of showed galaxy and different strong objects in the sky. Jan Oort, who was a professor in Netherlands, he thought that if there was a particular atom or molecules in space which can give rise to spectral line, then there is much more great deal that we can learn about objects, right? Because it's a different probe. That's one thing, and you know that with spectral lines we also get uh, an additional kinematical information which we do not get when we are looking at continuum emission, right? Because, for example, the relative velocity of a gas cloud with respect to Earth, like when we are observing, will found to be having a Doppler shift, right? Depending on whether that celestial object is actually moving towards us or away from us. So, just realizing the potential of such a possibility, he gave the problem to a student called Hendrik van der Hulst, his student, PhD student, to investigate like what are the possibilities, and he came up with this idea that there should be a line due to transition between two spin states of hydrogen atom, which you can see the diagram here. Like depending on whether the electron proton spin are parallel or anti-parallel, it gives rise to a line close to 1420 megahertz. To be precise, it is 1420.40572 megahertz, and this is called the 21 centimeter line because 1420 megahertz, when we convert it into wavelength, it corresponds to 21 centimeters. So we often use it as H1 21 centimeter line to separate it from other transitions like Lyman alpha or Balmer and other things which would happen at, for example, optical and ultraviolet wavelength. So this 21 centimeter line is a very powerful tool for studying the dynamics of galaxies, and it has led to discovery of, for example, dark matter, like studies of dark matter in galaxies. And then we know that galaxies evolve a lot by interaction with each other, and there are certain aspects of galaxies which are much better seen only through neutral hydrogen. In this image that you are seeing here of galaxies, in this case, you would see that like this is in blue we are seeing radio, and in and you can see that it is overlaid on optical. So you can see that there's large parts of blue gas here, which is neutral hydrogen seen in radio, has nothing seen in optical, right? If you just try to visually isolate those parts which are in optical, you will see that many of these galaxies would look actually just completely fine, and you would think that there is like just a quiescent galaxy here sitting doing nothing. But when you look at it in addition to radio, you put neutral hydrogen information, you find that no, they are actually interacting with each other. And this kind of process of galaxies interacting with each other form a very important part of evolution of galaxies. And all this is done at radio wavelengths. So next, detection of cosmic microwave background radiation is of interest to everyone, right? So theoretically, this was predicted by Alpha Herman in 1948, and they published a prediction that if indeed a universe were created in a Big Bang, then today we would see the glow of light. The glow of light that was released when atoms first formed. That's when, for the first time, it was possible for photons to propagate freely. So CMB is the oldest light in the universe. That's how we understand it. It dates from the first epoch in which photons could travel freely. Shortly after the Big Bang, the cosmos was very hot, right? That's the reason, right? But then eventually it cooled. So the black body nature of CMB, the curve that you see here, is actually characterized to 1 part in million, right? But even better than that, it's characterized to that accuracy, and it has a thermal black body spectrum. So this was also detected somewhat serendipitously. It was detected again by 2 engineers, Penches and Wilson, who were at Bell Labs, and they were again previously Jansky was trying to investigate some kind of noise in the communication signal. These gentlemen were also doing completely similar kind of exercise, and they found that actually this the static noise that is there in the signal is actually corresponding to cosmic microwave background radiation. And for this discovery, they were awarded a Nobel in 1978. And then next we come to discovery of pulsars, right? That's another very important discovery. It's a completely new field on its own. It opened up, and so how the pulsars were. So what are pulsars? So pulsar is but a highly magnetized rotating neutron star. You can see from this cartoon, and it emits a beam of electromagnetic radiation. You see here, right? But due to the fact that it is also rotating, this radiation is observed only when the beam of emission is pointing toward Earth. It is as observers, and as a result of it, the emission, although the emission is turning out continuous, when we observe it, it sort of gives it a feeling of a pulse, right? It's only when it is pointing towards us that we see radiation, and otherwise it is null, right? So we see some kind of a pulse signal. So first pulsar was observed on November 28, 1967, and this was by Jocelyn Bell Burnell. She was doing this as part of her PhD with Anthony Huish, and they observed these pulses, which were separated by approximately 1 second, roughly, and that always originated from a certain location in the sky, right? And again, like when you see some signal from the sky and which is peculiar, one thing that we straight away try to do is that, is it something terrestrial, right? Are we picking something terrestrial and some kind of a radio frequency interference, for example, coming from some device here? But they found that no, it was keeping to sidereal time. So this means that it is not of terrestrial in nature. And in looking for explanations for these pulses, they looked at various physical processes at that time, and they eliminated most of the astrophysical sources of radiation, such as stars and other things, right? And they also could rule out that it is not a man-made radio frequency interference because it was keeping to sidereal time. And they also observed with some other telescope at trying to see, okay, maybe my telescope has got some problems, so let us try to see with some other telescope. That's also a method used for confirmation often. That's why carrying out same experiment, especially of very major importance, scientists and astronomers always try to confirm it using different setups as well, right? So it also eliminated any sort of instrumental effect, right? That's also a possibility that one has to rule out. So at this point, they felt that, okay, it is coming from space, but what it could be, right? So in those days, like, and even now, like, we are all, none of us can rule out the possibility that there is another civilization in the universe, right? So that also crossed people's mind, and they thought, like, maybe it is coming from another civilization, and they called it like Little Green Man. That was the idea, or the name given to the aliens. But eventually they found not one, but more such objects over a period of time, and then they found that, okay, this is actually a certain kind of objects in the sky. It's called pulsars, because they're giving these pulses. And this discovery was then given a prize a Nobel Prize in 1974. As I said, like, this has since then grown into a field on its own. And further down the line, another 10 years or so, many more pulsars were discovered, and finally Hulse and Taylor discovered what is known as first pulsar in the binary system, and it's a pulsar which is actually going around a neutron star, and that allowed to conduct some very first test of, not very first, I will say, like, a precise test of the general theory of relativity, because general theory of relativity predicts that if the system in which, like, a pulsar is going around a neutron star, it should emit strong gravitational radiation, because the orbit will continuously contract, because as it loses orbital energy, so the pulse duration will change. So observation of the pulsar soon confirmed this prediction. So this provided the first ever evidence of the existence of gravitational waves, right? So as of so since then, like, observations of this pulsar continue to agree with general relativity too, right? So this was like two very important things it showed us. And in 1993, Hulse and Taylor were awarded Nobel Prize for this discovery. Right. So this is a very broad flavor of the kind of new discoveries and new science that radio astronomy has led to. Right. And you can see that starting from quasars, it's a completely different new field on its own, right? And then neutral hydrogen observation through 21 centimeter line. Now we can detect neutral hydrogen not just from Milky Way and nearby galaxies, but people are planning to detect it from the earliest stages of the universe. So you must have heard about of ionization experiments that are going across the world, and we will talk about a little bit more when we are talking about square kilometer array. That's one of the key science projects that square kilometer array would do, is which will be coming online in next decade. And cosmic microwave background radiation, like this discovery is one of the most powerful proof that the support for the Big Bang theory, that universe started with a Big Bang, right? Very important. And then pulsars, again, like very unique objects in their own right, but has also led to studies which has impacted our understanding of general theory of relativity and other physical processes, right? So radio astronomy has played a very important role in our understanding of various celestial objects and also cosmology. So it has a very broad impact. So if we talk about what kind of things that we have to do to detect radio waves, now you already have some idea of it because we have talked about the kind of experiment that Jansky was doing, then the type of telescope that Grothe Rebert developed, right? Just you can see a dish with a detector here, and then just sort of pointing towards the sky, so it collects the radiation, puts at the detector at the focus. So this is the kind of standard setup that you would expect that is being used at radio astronomy too. But then compared to other wavelengths, it has got its some specialities, and that's something. And those are very interesting. And those, as I was saying in the beginning of my lecture, are related to Young's double slit experiment, Michelson interferometry, and Fourier transform. And we'll talk about more of these, like the detectors, especially we'll talk about what a good radio telescope is or should be like, and what are its basic characteristics. And once we have that, and then what kind of then how do we detect actually radio waves, and how do we make images from that? So that will be the subject of next lecture. But in case you feel stimulated to know more about radio astronomy, I would say that you go back and have a look at some of the things which you've already done related to Young's double slit experiment, Michelson's interferometer, and maybe brush up some Fourier transforms, because now with this new insight, if you come back tomorrow with a little bit with those ideas refreshed in your mind, you will find it will be much more enjoyable, right? So that's one request I have. And this is my last slide for today. What you see here is a giant meter wave radio telescope. It's a telescope which is close to Pune. It's situated about 90 kilometers. So what is it made up of? It is made up of 30 dishes of 45-meter diameter, right? And it is spread over an area of 25 kilometers, right? So what I'm telling you today is that it's not that it's 30 telescopes. It's actually one telescope which is made up of 30 dishes, right? And it is a telescope which is kind of as large as 25 kilometers, right? So this can be, if you don't know the concept of radio interferometry, this can be a little difficult to accept, and rightly so, that how is this one telescope? You see 30 dishes here and it's spread over 25 kilometers, right? Like, so how does it work out, right? That this is made up of dishes of 45 meter, but spread just by putting it across 25 kilometers, do we get a telescope of the size of 25 kilometers? How do we understand this, right? So this is something which is related to radio interferometry, and that's something which we will talk about in more detail tomorrow, right? So for now we will stop, And if there are some questions, especially, let's take them and have some discussion related to today's lectures. So tomorrow we will talk more about detection at radio wavelength, radio interferometry, and after that, in the next lecture, we will continue with this theme, and then we will conclude with some of the modern telescope like spectrometer array that's coming up. Right, that's how we will conclude. But so specifically, if there are some questions related today, let's talk about them now. I'm going to stop sharing my screen so that I can look at if there's something comes up in the chat. So there are already some questions in the chat. So I'm going to, so I also see a raised hand. What I'm going to do is that I will quickly go through the questions that I see in the chat first. Okay, somebody was suggesting that it's better to have full screen mode. I agree with that, but what was happening that I was not able, my cursor was not visible then. I'll try to fix it. And because I wanted to point certain things on the screen, because otherwise it becomes slightly difficult to point out certain things. Somebody asking about like related to can we explain what is the non-thermal radiation? So non-thermal is just a term given to anything which is not black bodies. So you can think of it as a general term in that sense, because at that time when people were expecting that, okay, should have a black body spectrum, but when they didn't find, they thought like it is coming through not from a black body process, but it's coming from something like a non-thermal process. And then later it was understood around simultaneously, the theory was developed of synchrotron emission, that when electron is going, electric electron in the influence of magnetic field will have a trajectory which is helical path. And since it's going around in circle, it's continuously changing direction, right? So that's equivalent to acceleration. And you know that an accelerated charged particle will give radiation, right? So that's the basic idea, that through this process, which is called synchrotron emission, we are receiving radio waves. So somebody asked me why radio astronomy is non-thermal. No, I'm not saying that radio astronomy is non-thermal. What I'm saying is that there are also other processes than black body through which we receive radiation at radio wavelength. So it depends on what kind of object that we are observing and what kind of physical process that is taking place in that, and then we will be detecting thermal or non-thermal or a mixture of both, depending on that, right? So that's why we have to observe an object at different frequencies, right? Because then what happens that then we can look at how the what's the kind of spectrum that object has, whether it's a thermal, non-thermal, and we can try to decompose and understand what kind of physical processes that are taking place. Now somebody asked me, even though there are important radio sources from the space, there are many radio sources on the Earth too. How do ground-based telescope eliminate them? Right. So yeah, elimination is one good thing to do. The best thing is to avoid them. Right. So avoidance is done by two ways. One is that we go to places where we are away from such sources which are there on ground, right? So I will not set up my radio telescope sitting in Pune or in Delhi or in Bombay. I'll go to far off places. That's why, for example, GMRT is situated 90 kilometers away from Pune. Of course, that place now also has become very populated. But you will see that the next generation telescopes like square kilometer array, which are coming up, they are like completely away from civilization that way, like in remote deserts. Many telescopes will find a setup like that so that we can avoid radio frequency interference. Then another thing which is done is can think of it as cooperation, right? Like we kind of sort of talk to, for example, if mobile companies are coming up and they are setting up their receivers and transmissions at certain frequencies, we try to develop an understanding with them that, okay, we want to do radio astronomy at these frequencies. Can you sort of just do your signal, confine your activity to certain frequencies? So there's some kind of frequency allocations takes place for different activities. Right, so people have to take licenses and then do these things. So that's one thing. Another thing that is done, and then of course, even after all that, we do get data which will have a lot of radio frequency interference, then people develop a lot of computational and mathematical techniques through which that signal can be identified and rejected. Right. So the best is to avoid, but whatever then comes through is then has to be dealt with in computation. Somebody is asking, can you explain the H121 centimeter detection process again? So H121 centimeter line is a spectral line. So like any other spectral line, it corresponds to a condition between two energy states, right? So hydrogen, when it is in, so hydrogen is what? Electron, proton, and when it is in ground state, depending on, an electron proton will have a spin. So depending on whether this spin is parallel or anti-parallel, this corresponds to two different energy states, right? So the ground state is then split. So it's called hyperfine splitting. And because of this splitting, then depending on whether, and this energy gap between these two energy states is corresponds to a frequency of 1420.405 megahertz or 21 centimeter wavelength. So that's what this S121 centimeter line is. So now if I look at a hydrogen gas cloud and it is at a certain distance, let's say away from it, then the atoms which are there in the excited state will transit to ground state and they will radiate a photon, right? And that is something which I can actually receive exactly at 1420.405 megahertz. But if this cloud is actually moving away from me, then it will be redshifted to a lower frequency, right? So that's the kinematics or the Doppler shift part of it. So this is how this H121 centimeter line works. Can one work on radio and gamma astronomy hand in hand? Yes, of course. As I was showing through one of my slides, that there was this. We can at each wavelength, even about the same object, we can learn different things. So, most likely at radio and gamma rays, you would be looking at different astrophysical processes that are taking place in that object. So depending on what kind of object it is, it can be useful to look at both or not, right? So, for example, if you're looking at AGN or like a Blazar and that kind of an object, then those would be emitting at radio as well as at gamma rays, and there's something to learn at both the wavelengths. So if something is in a binary system, then it will be going around the center of mass, right? So then the pulse would actually get Doppler shifted periodically. That's how you would detect actually that whether it's a binary system or not. Somebody's talking about one filter persistent background radio noises that's related to interference. Yeah, so there are these different satellites that are going on in the sky, right? Depending on what frequency they will communicate. So Starlink and other projects, they are also putting satellites which will actually pollute not just the radio wavelengths, but also the optical wavelengths, right? Because there will be too many of them and they will be affecting astronomy at different wavelengths. So somebody is asking about projects. So about projects, I would say like it's better to write an email because that's the more detailed thing, and that's sort of like a one-to-one communication. That's what is needed. It's sort of not everyone is interested in that discussion, right? So I have pretty much now covered whatever there was there in the chat here. I could see some of the raised hand, but they have gone down now. If somebody still wants to ask, we have a couple of minutes. We can ask them now, or tomorrow also we will have an opportunity. Okay, so.
Hello, sir. Am I audible?
Yes. Please
so
go ahead.
My question was from the Janssen detections, the third faint object, which was coming from the center of the Milky Way galaxy, which was pulsating. Could you just explain the nature again, like why it was pulsating? Because it was coming from a center, and what was causing this pulsating nature?
No, it was not pulsating because the object itself was pulsing. It was sort of scanning the sky, right?
Yes.
Right. So at certain location in the sky, this emitter is there. So when he is pointing towards there, the strength of signal will go up, right?
Yes.
And then he moves away, it will go down. So when you will make a graph of this signal, it will show a profile like that, right? And then of course every day this object is also moving, right?
Yes.
And that is moving at a sidereal rate, and that told us that okay, it's astronomical, so it's not something terrestrial, right? So that's what it was, not pulsating. It was because we are scanning the sky, but we are not continuing.
Oh, it was shifting from the telescope was shifting, and at every day
the telescope
it was just
scanning sky because he was trying to understand where it is coming from.
The peak was coming from the center itself.
So that's where. So the peak was from the Milky Way center.
Yes,
right. That was so he was scanning the sky to see kahan se aa raha hai wo. That was the thing.
Okay.
So initially, when he was starting, then both the things were co-located close to. It happened that the sun was also close by. So initially, he was confused that it may be coming from sun. But then, as you know, that slowly then it sort of shifted. They got separated over a period of few months, right?
Yeah.
Okay. That's what happened.
Yeah. Thanks.
Yeah. Yeah, if someone else want to ask a quick question, we can. Otherwise, we can stop now because I understand that you must be having other lectures also, so you would need a break as well. So I do not see anything more. Okay, it was great fun. I think so this was a good pattern. We will do this tomorrow also. Last 10 minutes we keep for questions and discussions. That's the way it is. And yeah, so see you tomorrow. Bye for now.